Well, good morning. So, first things first. If something supposed to work, there's no excuse for that not working. So I've prepared, to save time, the seals and try a different tube. The first one was white. This is greenish. I hope the color will affect the physical phenomenon. Will it? So, you know the drill. Open, turn, count 60 plus 30, about 90 seconds. In the meantime, now, what was happening again? The airflow below has more obstruction, so slows down relative to the airflow above. When it travels fast, the pressure is lower, higher pressure, lower pressure, stronger force. Weaker force, net force, pushes it up, holds it, and it flies. Prepare. Prepare. Well, let's hope it's going to work today. I don't want to do it tomorrow. All right. Well, it did work, and I'm happy. It proves correct. It proves that physics does work if you do it right. Now we can move on to our current topic. Gravity. So, solving problems, because technically we don't have to learn anything new theory-wise. Theory has been covered. And question to you. This is an example. We need to use the law to calculate the force of gravitational attraction between a large planet and a small object. In this particular situation, the Earth and a 1 kilogram weight, which is placed on the surface. So you should draw a picture of the Earth, which looks like this. And there is a tiny object right on its surface. And the question is, how strong is the force of gravitational attraction? First of all, does the Earth attract this little object? Of course, we know. Does this little object attract the Earth? What do you think? The Newton's third law says any two objects, when they interact, exert forces of equal magnitude on each other. So, of course, they interact each other and attract each other. And the difference is that a tiny object can't influence significantly the motion of a large object. So when we jump, we push on the Earth, but the Earth doesn't care much about it. But of course, when the large object is acting on a small object, the influence is strong. So here, if we want to draw a picture, that should be a large circle which represents the Earth and the tiny object sitting there. And we know that the distance from the object to the center is that distance which has to be used here. And we know the constant. The constant which is described by the capital G has a name, a universal gravitational constant or gravitational universal constant. It's a constant, it's a fixed number, and you can see that the power is -11, so it's a relatively small number, and that means that force of gravity is actually very, very weak. But if it's weak, why do we feel it so strongly? Because it's exerted by a huge object, by a huge mass. The mass of the Earth is 6 times 10 to the 24th kilogram. We cannot imagine this number is too large for us. So, by now, probably you already finished calculation. So let's see what's happening on a web assign. Good thing I have 2 hands. So this is what we are looking for, the magnitude of this force. Well, the thing is that from the perspective of that tiny object, which is basically us because we are tiny relative to the Earth, sometimes that makes feel us a little and insignificant. Yeah, but the Earth is huge. What can we do about it? So, from our perspective, we just see huge flat surface, and we know that on the surface of the Earth, to calculate force of gravity, all we have to do is this. So, 1 times 10 newtons, done. Of course, the question is, would we get exactly the same result if we used the Newton's law for gravity? Well, in that case, we would have to plug in numbers. .67 times 10 to the negative 11, 1 kilogram, about 6 times 10 to the 24, and keep forgetting, about 6 times 10 to the 6th, 6.4 times 10 to the 6th. What do we do with it? What do we do with this number? Very important mathematical symbol, parenthesis, because we have to indicate what do we want to square. We have to square the whole number, not just 10 to the 6th. Now you take a calculator, take a calculator and calculate it. Of course, you get the same number. So this is just an exercise for you to use your calculator. We know the result supposed to be 10, because that's how we calculate force of gravity on the surface all this time. So this has to be consistent. And the real reason for this question is proving that the acceleration due to gravity is indeed equal to 9.8 or closely 10. So how would we calculate the acceleration due to gravity using the Newton's law for gravity? Well, we would have to imagine that we have an object released from rest, for example, at certain height from the surface. And we could apply the Newton's second law first. Net force supposed to be equal to mass times acceleration of that object. Neglecting friction, the only force acting on it is force of gravity. So the net force is that force. It should be equal to constant times product of masses divided by the distance from the object to the central point, center of the planet, the Earth. And it should be equal to the product of the same mass. This is the mass of the object. This is the mass of the Earth, of another planet, times acceleration. And what we see immediately is acceleration doesn't depend on the mass of this object. Plus, we see that the acceleration depends on this altitude, h. However, if we are very, very close to the surface, we can neglect the altitude relative to the huge radius, 6 million meters. In this case, the number should give us the free fall acceleration. And again, at this point, all we have to do is just plug the numbers in and calculate. And of course, no doubt, calculation gives 9.8 meters per second squared. So this example tells us how to calculate the free fall acceleration on any planet or even star. And plus, it proves again, mathematically, that it doesn't depend on the mass of the object. Doesn't matter if it's heavy or light, it falls down with exactly the same acceleration. It increases speed by the same amount in second, every second. Well, as an example, let's see how acceleration changes if we go up higher and higher. Well, acceleration, as we just have derived, should be equal to a constant times the mass of the Earth times the distance squared. And now distance has two parts, the radius of the Earth and the altitude. So we just have to plug in numbers, 6.67 times 10 to the negative 11. The mass of the Earth is about 6 times 10 to the 24th. The radius is about 6.4 times 10 to the 6th. And now we have to add 20 kilometers. How do we know? We can see, yeah, we can read. 20 kilometers, we need to convert into meters, so it's 20 kilometers squared. All right, for me, it's time to get my coffee, and for you to finish calculation and tell me a number. That's it. For God's sake. Sit. As soon as you have a number, just scream it out. Bless you. If you didn't succeed first time, right? However, if you try and again and again and again and doing exactly the same thing, expecting different results, that's not going to happen. So please, anybody, tell me a number. So it decreases, of course. We could sketch a graph for acceleration as a function of altitude. And when the altitude is 0, the number starts from 9.8. And then it should gradually decrease. Well, theoretically, eventually to 0 if we move infinitely far away. That's it. Any questions? So, next typical situation, when we have several objects interacting. In this case, well, we launched a satellite from the Earth to the Moon. Of course, in reality, it doesn't travel just straight from the Earth to the Moon. It travels in spiral, eventually speeding up, and eventually reaching certain speed. But we can imagine that at certain instant, this satellite is exactly at the middle point between the Earth and the Moon. So you can search online for the distance between the center of the Earth and the center of the Moon. It's about this number in kilometers. We know the masses have been measured, and the satellite is right here. So, how many forces act on the satellite? 2. The Earth attracts it back to it. This is the force number 1. And the Moon, actually we can tell immediately what should be the direction of the net force. If we look at the Newton's law for gravity, it depends on masses and distance. But if the distance from the object is the same to both planets, only mass matters. And of course, the Earth is much heavier, so it exerts at that location stronger force, and the net force points toward the Earth, but the engine pulls it away. Well, anyway, if we want to calculate the magnitude of that net force, magnitude of it, we have to subtract 2 magnitudes. And if we want to subtract those magnitudes, we have to calculate each. And what would we do to do that? We would apply the law twice. Same constant, the mass of the satellite, the mass of the Earth divided by, well, if we use this distance, we have to write 1/2 of it squared. And I need to subtract, same constant, same mass of the satellite, and this is the mass of the Moon, and divided by same distance squared. And that's it. I'm not going to do any calculations at this point. You just take in a calculator. 1 metric ton is equal to 1,000 kilograms. Plug in numbers, and calculating would be easy. And again, the net force at this instant would point to the left. And this is a week 2 material, and we are in a week 6, so moving on faster. Question. A satellite is orbiting a large planet, central mass, and at this particular instant, how does acceleration point? acceleration of this satellite. How does it orbit it? Clockwise or counterclockwise? We have no idea. Does it matter? Absolutely not. So we just have to again refresh in our memory something we know about this type of a motion. And we said this type of a motion, this type, so we start thinking, what type? Is it a linear motion with constant velocity? No. Is it a linear motion with constant acceleration? No. Is it a projectile motion? No. If we look at the shape of a trajectory, that is circular motion. Technically, we have two types of circular motion, with constant speed and when speed changes. So when speed changes, there is a tangential acceleration, angular acceleration. When speed remains constant, tangential acceleration is zero, angular acceleration is zero. But the acceleration itself is not zero. And if it's not zero, it has to have a direction. It has to point somewhere. And survey says it points at that particular instant, at that particular location of the satellite. Up. Because since we can read and understand the meaning of special words, this is a special type of the motion, a uniform circular motion. And the uniform circular motion acceleration is equal to centripetal acceleration. And centripetal acceleration has two properties. It points towards the center of the circle, and it has magnitude of speed squared over the radius. So if the object is, well, here, it is up. Week 3. So far nothing new, right? Which makes our life easier. Well, now, of course, we need to apply all this knowledge to analyze a specific situation. So satellite is orbiting. What can we calculate? If it's a circular motion with constant speed, we can calculate a period, that speed, centripetal acceleration, force, if we want to. We just have to follow all the strategy we used 2-3 weeks ago. So the acceleration instantaneously points, well, almost to the left, toward the center. And immediately, if we said acceleration, we have to relate acceleration, force, well, net force, mass. And net force is, in this case, is equal to the force of gravitational attraction because there are no other forces. So the law says, well, 2 Newton's law together, second and people call it fourth, say that the product of the constant, 2 masses over distance squared should be equal to mass times acceleration. Not a new equation. Not a new equation. We used it several slides ago. Turns out that this centripetal acceleration is just that free fall acceleration of this object. So it is constantly falling, but constantly missing. That's why it keeps falling forever until, well, the atmosphere or gas, which well, hydrogen normally in the space beyond the atmosphere slows it down and it falls down. So again, we can cancel the mass. So in this situation, if we don't need to know the force, mass doesn't matter. And the acceleration is equal to speed squared over the radius. So we can cancel one radius. The expression, which we can use in the future, tells us how to relate speed squared, the mass of the planet, and the distance from the center of this planet to the satellite. Don't be scared. We will solve this problem. And of course, in general, we have to know the altitude. The altitude is given 20,000 meters. And we know the radius of this planet. We know the mass of this planet. So we can calculate speed squared. What do we do with that? First, we can calculate immediately kinetic energy of the satellite, because kinetic energy equals mv squared over 2. Second, we can calculate that speed. Just take a square root of this, right? So what do we want to explore first? Let's do energy. mv squared over 2 will be equal to, so kinetic energy will be equal to m over 2 times, and speed squared equals constant, the mass of the planet over r, over distance. Of course, we can rearrange these variables, write 1/2, then constant, the product of the masses over r. And now, you may not remember that, but we saw this equation on Friday, twice, when we said that the exact expression for potential energy looks like this. This expression, well, is expression based on the one natural assumption. If we remember, we can measure potential energy from any energy level. We can choose the origin anywhere. So this expression assumes that the energy infinitely away from an object equals 0, which is natural. So when we move two objects away from each other, eventually, when they are infinitely far away, the energy should be 0 because they don't feel each other anymore. So if we compare this expression and this expression, turns out kinetic energy of the satellite and potential energy of the interaction between the satellite and the planet related. For example, kinetic energy will be equal to 1/2 times negative u, negative potential, because we can just compare a symbol by a symbol g, little m, big M, r. So this whole thing should be equal to negative u. That's it. Sometimes it's a very good relationship, because if we know kinetic, we can calculate potential immediately. If we know potential, we can calculate kinetic immediately. But now, if we know kinetic and potential, what can we calculate? Total mechanical energy equals kinetic energy plus potential energy. So for example, we can write it in terms of u, right? Kinetic equals negative u over 2. Potential, just same u. U minus 1/2 of u. 1/2 of u. That's it. So this again tells us that if we calculate potential energy, just divided by 2 gives total. Now, potential energy is negative. Constant is positive, mass positive, anything distance is positive. So in multiplying by -1, potential energy for two interacting objects, negative, because they attract each other. And which means total energy also negative. That's a negative number. That again is an expression of the fact it's so-called bound system. If we want to take it apart, we people have to do work on it, positive work. It can survive technically forever until something starts acting and pull them apart. Well, all done with energies. Now we can explore the information about speed. If we know speed and we know distance traveled, we can calculate how much time it takes. Distance traveled, of course, in one period is equal to circumference. It's a standard circular motion. So, too soon. Let's insert a slide. Do I still have it? Have it. Okay. So, this is the orbital speed. We need to remember that what is happening is the satellite travels about the planet, not fly away from it, not flies away from it. So the radius, the altitude, and this is that little r, which represents also the radius. But that's the radius of the trajectory. And big R, capital R, is the radius of the planet. So when you say this word radius, that's ambiguous until you specify radius of what? Radius of trajectory, lowercase r, which is equal to the sum of the radius of the planet plus the altitude. Well, in one period, it travels distance equal to one circumference, 2 pi r. And this very speed should be equal to distance over time. So 2 pi r over this period, which means we can calculate the period 2 pi r over speed. That's it. Well, if we want to, we can try to rearrange the variables using some algebra. Speed is equal to square root of this expression, square root of product constant, mass of the central object of the radius. So it's going to be 2 pi r, 1 extra r, and it's going to be square root of constant times mass. Now, there is something very, very not wrong, but bad about it. Square roots. What do? We don't like them. So what do we do to get rid of square roots? Square. So we can square the whole expression. Is going to be the period squared on the left and 4 pi squared r over the product of constant and mass. Or this is how we can rewrite it. Bless you. And this combination of variables, bless you again, doesn't depend on the satellite. It is fixed by the central object, by the mass of it. So for example, if we have another satellite orbiting the same planet or the same star, for that satellite, the equation for the period squared, hat, will be equal to same number 4 times same pi squared over same constant over same mass times the new radius cubed. And now, if we divide these expressions, we get the Kepler's law, the ratio of squares of the periods for two satellites orbiting the same central object is equal to the ratio of the cubes of their radii, or radius, as people say it differently. Well, of course, Johannes Kepler derived this law purely from observations. It took a long, long time for him. And he used data of Tycho Brahe. And then Newton used those data to come up to derive the expression for his laws. Now we can go to this slide, which is the summary of everything I just said. Now we can calculate the orbital speed for this planet. If a satellite is spinning about the Earth very close to the surface, so we neglect the altitude, it has to travel at 8 kilometers every second, at least, or faster, in order to keep missing the Earth. If it slows down, eventually it hits the Earth, it falls on the surface. Well, okay, let's do it as a review of everything we just said. So we know that the speed of a satellite is defined by the mass of the central object and the distance from the center of the central object to the satellite. And if we need to calculate this ratio, we just have to write the expression for the speed twice. The beauty of this problem is that the central object is the same, so the variable capital M is the same. All we have to do now is just calculate the ratio, literally. First speed divided by second speed, so we write General Motors over radius, General Motors over second radius, and immediately we can cancel constant, we can cancel mass, we can rewrite this as a different ratio. And now we just have to use the picture. In this picture, this is the altitude h2, which is equal to 7 times the radius of the planet. But for the radius of the trajectory, we should add one more radius. So it's going to be equal to 8, capital R. And R1 will be equal to 2 times R. And the answer is 4. Square root of 4, 2. So the first satellite will be traveling twice faster than the second one. Well, natural. It takes more time for the second to travel longer distance about the same planet. Any questions? And of course, you can apply this type of reasoning to calculate any type of a ratio for the periods, kinetic energies, potential energies, mechanical energies, or else accelerations, forces, Every time the constant, gravitational constant g and the mass of the central object m will be cancelled, and everything will be related just to the ratio of the distances, maybe to the certain power, square root 3 second, something else. This has nothing to do with physics anymore, just pure algebra. Well, so the orbital speed is the speed the satellite needs to spin about the planet. Next question is, how fast should it travel to leave the planet, to fly away from it? And to calculate that speed, all we have to use is conservation of energy. So we can imagine that the satellite has finally reached that speed, which has a name, escape speed, and start flying away. Leaving means, mathematically, being infinitely far away from the central object. The speed which is sufficient for that is such that at the infinity it stops moving. The final speed is 0. If the initial speed will be higher than that critical we're looking for, that means at infinity it still will be traveling. So if the object has that initial speed sufficient to escape the planet, and of course we initially neglect any altitude, so it starts from the surface. The energy, mechanical energy of this system will be equal to kinetic energy of the satellite plus potential energy of the interaction, gravitational potential energy, initial. Okay. But when this satellite is infinitely far away and it stops, the mechanical energy final still is equal to final kinetic plus final potential, but kinetic is 0 because it stops, and the potential is 0. This statement needs an expression for potential energy. So we have to write it down explicitly. It's negative, universal constant, the product of the masses over the distance from the satellite to the center of the planet. And we can see this expression, g m little m over r, should go to 0 eventually when the radius increases. Eventually, potential energy reaches 0. Why? Because we chose potential energy at infinity to be 0. Now we say no friction, of course, so mechanical energy before and after is conserved. And the equation says mv initial squared, this is the speed we are looking for, the escape speed, minus g little m big M over r, potential energy of the interaction, should be equal to 0 plus 0, 0. That's it. Now we have to cancel the mass again and solve it for that speed. That's the minimum speed necessary to escape, to leave the central planet. And for the Earth, it's about 11 kilometers per second. So to orbit the Earth, you should have 8 kilometers per second or so. Then you start speeding up, travel faster and faster and faster. Your circular orbit becomes elliptical and eventually hyperbolic when you reach 11.2 kilometers and you can fly away. But, of course, you still cannot escape the solar system because the sun holds you. So there is a second escape speed, next escape speed, which has to be reached to escape the sun and fly away to other galaxies. And everything based on very, well, kind of simple theory right now, and especially simple algebra. Yeah. In Newton's time, that would give you a PhD. Now, people learn it in 9th grade, at least in certain countries. Any questions about gravity? Next topic. We start talking about temperature and properties of gases. And what is temperature? Well, first of all, a temperature is that feeling we experience every single day, every single minute. Yeah, it's cold or hot. How do we feel it? Well, through our sensors in our skin. We actually can change our feeling if we rub our hands against each other. So, of course, we're not very accurate measuring devices. So to measure temperature, people have invented many, many different measuring devices like this, or smaller version like this. And we can change the temperature by using some energy. The most accurate measuring devices look like this, but much smaller. This is an electronic thermometer. So if I have to use it, I have to plug it in. The smaller version has a built-in battery in it. And this wire at its end has, well, it looks like a needle, but in reality, there are two different wires made of different metals welded together. This device has a name, a thermocouple. And I have a thermocouple here attached to a lead bulb. Why do I need to attach it? Because that's the only way to measure temperature. We have to bring into contact the object temperature which we want to measure and the measuring device. Well, sometimes optical contact. This is infrared thermometer. You can read the number 70. The temperature here is about 70, well, Fahrenheit. It emits infrared light and it reflects back and it measures the temperature. So we have developed, well, we people have developed many, many different temperature scales, but only 3 survived. The most popular in the world is temperature scale measured in Celsius. The least popular in the world, the temperature scale in Fahrenheit. And the most popular in physics, the absolute temperature scale in Kelvin. So of course, if we know temperature using one scale, it's just a matter of using conversion factor, in this situation, conversion equation, to relate any two temperatures. Well, right now, this ball has temperature of 20 degrees of Celsius. Let's see what's going to happen if I place it into hot water. It starts changing. It doesn't jump immediately to the actual temperature of this water, so it takes time. Every process takes time. There's inertia in everything. But eventually, the temperature stops changing. When that happens, we say the thermal equilibrium has been reached. That's it. And how do we set a temperature scale? Well, Celsius just used 2 buckets, one with iced water, second with boiled water. He placed his thermometer into iced water, drew a line and said 0. He placed the same thermometer into boiled water, drew a line and said 100. And then divided everything by small 100 equally spaced units. That's how the Celsius scale has been developed. And because it's based on 100, that's the most convenient. That's why almost everybody else uses it. But these equations tells us how to relate, how to calculate the same temperature in Fahrenheit if we know Celsius, and in Celsius if we know Fahrenheit. And that capital T represents the so-called absolute temperature. The meaning of it we'll learn later, but basically it's related to the motion of molecules. The absolute temperature is temperature such that when it's 0, molecules stop moving. Well, and what is good about the absolute temperature, it is linearly related to the Celsius temperature, which means even if they different in degrees, the change in temperature is the same for both. And if we use degrees of Celsius to measure temperature in Celsius, and using degrees of Kelvin to measure absolute temperature, the change will be the same in Kelvin or in Celsius. And sometimes that confuses people because different sources online or textbook, when they calculate temperature change, they may use different units. Some might write Kelvin, some might write Celsius. Turns out for the temperature difference, it doesn't matter. Now, all original methods to measure temperature based on the fact that temperature affects the size, the volume of objects. Normally, when we heat an object up, it expands. It becomes larger. If we take a meter stick and heat it up, it's getting slightly longer. And the elongation, the change in the length, is directly proportional to initial length and the temperature change. And you see in this slide, the temperature change is written in kelvins, but we know that we always can replace it immediately in Celsius, because temperature change will be the same using both scales. The coefficient which has a name, coefficient of linear expansion, of course depends on internal properties of that material, has been measured for all important materials. And sometimes instead of a Celsius degree, you may see Kelvin degree, but it will not make any difference. Now, this is a very common demonstration. When we heat up a single metal, because the coefficient of linear expansion has an exponent -6, it's very, very difficult to measure. But what we can do, we can weld together two different metals, brass and aluminum, for example. They have different coefficients. And now, if they warmed by the same degrees, they will expand differently. And how does it affect the device? It bends. One expands more than another. And how do we use this? Well, of course, the bending depends on the temperature change. So, depending on the bending, we can figure out what the temperature is. The device like that has a name, thermostat. First thermostats were based on this principle. Of course, they used more sensitive coupled metals, but so when it heats up, it bends more, and the reading, the needle shows the temperature. Question: what do you think is going to happen if instead of just a strip, I will have a ring? I will be heating it up. Right now, this ring and this ball hope that's the right pair. All right. This ring and this ball, not a good fit with each other. Yeah. So I'm going to heat it up, and only three things might happen. Nothing. The ring shrinks, so the ball will be even harder to get through. I don't want to do it, but I can put it through by my force. Or the ring expands, and the ball easily gets through. So all I have to do is just do. And you should enter what you think, what's going to happen before I do it. What do you think is going to happen? I wasn't able to hear you because of this, but you're right. Well, it's a ring. So actually, it's more like a linear, one-dimensional object just bent. And one-dimensional objects clearly should increase the size. So this ring should expand. And now the ball easily gets through. And of course, if I cool it down, it's hot, so water evaporates. You can see the vapor. But if I cool it down, well, of course it should shrink back. Well, I'm not sure. Yeah. Yep. Again, may be used to measure temperature depending on the size of this ring. Now, if we have a plate which expands, in that case, both sides expand, and so the area enlarges. If we have a large three-dimensional object, a cube, of course, each side will expand, so the volume expands. And this is why the thermometer works, because we have, well, originally it was mercury. We heat it up, the volume expands, and we can see the level changes, and if we graduate it, that's how we can measure temperature. And if we want to calculate how much the volume changes, we just have to take the equation for the linear expansion and cube it. Length times time width. But if we cube it, these terms, quadratic and cubic, so tiny, so small, we can neglect them because the change is fraction of a millimeter normally. If you cube it, it's a fraction of a fraction of a fraction of a fraction of a millimeter. So the expression for the volumetric expansion is very similar to the expression for the linear expansion. This coefficient used to be called beta, the coefficient of volumetric expansion. But eventually people realized we don't really need to measure it. We just have to take a coefficient of linear expansion and multiply by 3. Well, any experiment with temperature you saw was related to energy exchange. For example, I plugged in the power outlet, the electric kettle. So the energy was produced at the power plant away from here, transmitted here, and I used it to warm up the water. Then I poured it into the cup. Hot water and cold lead ball were brought into thermal contact, and when that happens, the hotter object loses energy, the colder absorbs some energy, energy exchange is happening. And of course, we need to assign a specific variable which describes the amount of energy being transferred from one object to another. We call it heat. And we know it's energy, so we can measure it in joules. But historically, this amount of heat also been measured in special unit calories. And objects don't have to be in direct contact in order to transfer energy. For example, if you bring your hand close to a bulb, you feel the heat. But in all our experiments, we have to place objects together so molecules could interact. Molecules interact and transfer energy. Question. Imagine. And to do that, you have to use your imagination. So you are at home. You open the freezer, take a piece of ice from it. You have a heat plate. You turn it on. It becomes red. And you place a piece of ice on a heat plate. And you wait. You look at it. You look at it, observing what is happening. Your friend enters your room and says, when an ice cube is taken out of the freezer and placed on the heat plate, it immediately starts melting. And you say to your friend, and these are your choices, what you can say to your friend. Well, in reality, there are more choices. And I want to see the most popular choice. So what do you think? Why? Yeah. You said 2, I saw it. Now please tell me why. Because everything takes inertia, as we saw. Everything takes time. And more importantly, you're right. This statement is wrong. It doesn't start immediately melting. Melting or freezing, boiling, those words describe situation when the material changes phase from a solid to a liquid or from a liquid to a gas. And every temperature, every phase change happens only at a certain temperature, which has a name, temperature of phase change, temperature of melting, of temperature of freezing, or temperature of boiling. And for ice to start melting, the temperature should be equal to what number? In Fahrenheit or Celsius or Kelvins? By the way, that's the same temperature when water starts freezing. So, someone should say it loud, not whispering. Say it. 0 in using what? Celsius or 32 Fahrenheit. It's exactly correct. But in a freezer, the temperature is about -5 Celsius, -3 Celsius. So when we take it out of the freezer, the initial temperature is below 0. And it just can't start melting until it reaches 0. So at first, it takes certain time to reach the phase transition temperature. This process has a name, temperature change, because it changes from not 0 to 0. And then a new process starts, phase change. It takes a certain time. It starts from having a piece of ice. Eventually, it ends with having just a puddle of water. In between, it's a mixture. But now, what starts happening when everything is melted, this new substance, water, starts warming up. Can it be warmed up infinitely high? No. It reaches which temperature? 100 of Celsius or to 12 Fahrenheit. And then it starts boiling, evaporating. How much time does it take? Depends on the amount, but eventually it evaporates completely. But it doesn't disappear. We get gas, vapor. And if we keep going, that vapor now increases temperature. Eventually, we can turn it into plasma, but that's going to be a completely different topic. So, temperature change, phase change, temperature change, phase change, temperature change. These are only two processes which might happen with any substance. And of course, for each process, we need to know how to calculate the amount of energy spent or absorbed. In this particular situation, absorbed, because in order to be warmed up, that piece of ice has to gain some energy from hot water, for example, or from a heat plate. And then in order to melt, it also has to gain, absorb energy. Well, the amount of energy required for a specific temperature change, and that's what we call heat, and use a capital Q for that, is proportional to the mass, the amount of the material, and the amount of the temperature change. And the coefficient depends on the material. And this equation can be used for any temperature change process. And now phase change, of course, also related to the amount of the material. There is no relation to temperature because it doesn't change, it remains constant. But the phase changes, and how fast it happens also depends on the properties of the material. So some constant related to the material. And these constants, of course, have been measured. They know names. lowercase c has a name, a specific heat of the material, and capital L, the heat of fusion. It's on the next slides. Now, of course, we can reverse the process. We can start from vapor and, well, of course, it has to be in a certain vessel, confined container, and then we start taking energy away from it. So we put it in a freezer, for example. At first, it cools down. That process has a name, temperature change. Then it starts turning into water, not wine. And it releases more energy. And then it completely turned into water and cooling down to 0 and starts freezing, turns into ice, and then cools down to a certain temperature. And of course, it doesn't have to be water. It could have been any material, any. We can take a piece of lead. It's solid, but eventually we can melt it up, make it liquid. And if we keep putting more energy in it, we can create gas of lead, gaseous lead. So these are only two processes which might happen with an object: temperature change and phase change. And this is the equations I just wrote, plus one more. So I wrote this equation because this variable has been measured and tabulated. A specific heat of water, about 4,000. A specific heat of lead, Google it, and another number. But this product of a specific heat of a material and the mass of that object also has a name, heat capacity, or capacitance, people say differently, of an object. So there's a little linguistic difference between calling little c and big C. This is a feature of a material, of matter. This is a feature of an object. Now, when an object absorbs energy, Q, the amount of heat, is positive. When an object releases energy, Q, the amount of heat, is negative. This equation, or that equation, takes care of it automatically. For example, water is warming up. Final temperature is above initial. This difference is positive. Water is cooling down. Final temperature is below initial. The difference is negative. But this expression has to be taken care of manually. This product, well, latent heat, heat of fusion, is a specific number, always positive because it's constant. Mass is always positive. So formally, this product is always positive. However, you should choose a plus or a minus for an actual value of Q. How do you do that? You have to base on what's happening. If you know the object absorbs energy, for example, ice melts, so Q has to be positive. If you know the object releases energy, for example, water freezes, you have to write a minus by your own hand in front of it. Well, now we're done, technically, with everything related to heating, cooling. For each process, we have an equation. You see the difference between this slide and this slide? Absorbing heat. So this graph represents processes which begin from lower temperatures, and system is absorbing energy. Everything is positive. On this slide, we begin from higher temperature. System is releasing energy. We don't have to do anything with this equation. Automatically negative, but we have to manually add a minus sign to that equation. Well, so the summary, another summary, just to take a mental photograph. Another summary. An example of different values for specific heat. You can see, for example, the difference between specific heat of gold and specific heat of water. Specific heat of water is huge. So if we want to change the temperature of water by 1 degree, we have to use a huge amount of energy, which is good, actually, for us. Otherwise, we wouldn't survive on this planet. Now, the last theoretical notion. If we have several objects put together into the insulated container, like a styrofoam cup, like this. So we can pretend that the processes inside happening relatively fast, so there is no energy exchange with the surrounding. In that case, the total amount of energy inside this system always has to be the same, should be conserved, which means eventually, when the thermal equilibrium is reached, they all should have exactly the same temperature. The hot objects get cooler, the cold objects get hotter, which is good for them. Yeah. Everybody is eventually equally warm. And of course, for each process happening in that system, we can write that equation for the amount of heat which one object releases or another object absorbs. And because the total exchange is not happening, if we add the amount of released and absorbed energies, the result should be equal to 0. And this equation has a name, the heat balance equation, which basically is a representation of a law of conservation of energy. There are two types of the equation. When we write it like this, each term is positive or negative depending on the actual process. That's why if we add them up all together, the result is 0. Positive and negative cancel each other out. There is no heat exchange. Or people write it like this. They use magnitudes for all of them, but they say that the total amount, the energy absorbed by one part of the system should be equal to the total amount of energy released by another part of this system. Heat balance equation. I don't know why is it happening. I did everything I was told to do by Google, so it wouldn't be happening, but it still keeps happening. Anyway, this is the final summary. And now you can just apply all that theory to solve any specific problem related to temperature change, heat exchange. So you're ready to do this, which means we just have to start doing some particular examples. Don't answer this question. Let's just go through this problem together. So what is happening? A solid object, a piece of lead, solid piece of lead, that's a bullet, flies at 100 meters per second and hits a target and stops. This is the initial situation. And the final situation, it completely stops. Of course, it deforms, but the question is, will it remain solid? Maybe it will partially melt, maybe completely melts. So what might happen? First of all, if it flies, it's a mechanical object. It must have specific amount of kinetic energy, mv squared over 2. The mass of this bullet is in kilograms, 0.01. Speed is 100 meters per second. We have to square it, divided by 2. So that gives 50 joules. When it stops, final speed is 0, which means final kinetic energy is 0. But we know that energy can't disappear. Mechanical energy can change, potential energy can change, kinetic energy can change, but energy in general cannot disappear. So where does it go? Well, when it deforms, there is internal friction. And of course, there is possible friction between the bullet and the wall or target. So natural assumption is all kinetic energy is transferred into internal energy of this bullet. Nothing goes to air, nothing goes to wall. So the initial kinetic energy is turned to heat. So the amount of heat this bullet absorbs will be equal to 50 joules. Well, how does it affect the temperature change? That depends on the material. It's lead. That's why we need more information. We need to know specific values for lead. Where do we find them? Google, I don't know, Bing, wherever you prefer. Ask. So, mv squared over 2 should be equal to, well, I'll write an equation first, okay, delta T. In fact, sometimes we don't really need to know the mass, because if you write an equation like that, we can see mass canceled. And the temperature change should be equal to V squared over 2 times C, which is 100 squared over 2 times. So you have to be very careful with units. An official unit should be joules per kilogram Kelvin, because that's what it is. C equals Q over M times delta T, Q energy in joules, M mass in kilograms, delta T in kelvins of Celsius. So, but this expression gives for C 0.12 joules per gram Kelvin. So we need to convert gram into kilograms, and that gives 1,128 joules per kilogram Kelvin. And actually, we had a slide with this number before. So 128. Now we have to take calculator and calculate. So 1 and 4 zeros divided by 256 equals 39, right? Kelvin or Celsius. How do I choose what do I want to use? That depends on the initial value. The initial temperature is given in Celsius, so I prefer using temperature change in Celsius as well. So final will be equal to initial plus change, which is 20 plus 39, 59 degrees. Now, is it reasonable Yes. If we look at the melting temperature of lead, it is 327 degrees Celsius. So of course, it remains solid, just deformed. But if it would have been traveled much faster, it would store much more kinetic energy in it. More energy would lead to higher final temperature. You have a question? Yes? Yes, that's exactly what I said. No. Because due internal friction, and we're ignoring friction between air and wall, everything is happening only inside the bullet.
All of that, because of the friction, all of that.
Because of the internal friction. So it doesn't stick to the wall. It deforms and falls down. And remember the demonstration when I was crashing cans? That's what internal friction is about. So when the parts of the bullet move relative to each other, they touch each other, that's what internal friction is, which means all energy change happening inside. In reality, of course, there is air friction, which takes away some energy. There's a friction between the bullet and the wall, which takes away some energy. We neglect that. But if we neglect that, the only process happening is inside it. All right, so of course, water is the most important substance for us. And I'm going to finish right now. I just want to point at different ways people write units for the same constants related to water or ice. It's important because sometimes just missing a unit leads to a mistake. So a standard unit is joule per kilogram Celsius. And when you do homework, you have to use exact values. But in a classroom or an exam, we're going to be using rounded up values because it makes calculations easier. So homework, class. All right. Thank you very much. I'll see you in a minute or two. Well, if you come to office hours. Don't forget lab 9 today is in B9 downstairs.
I came early to talk to you, but you weren't here. Exam problems?
Yes, that's good right now.
Okay, so maybe we'll have this hour.
We can meet you in about 30 minutes in our office hour room.
Okay, I'll be there. Thank you.